So to kick off the first of this afternoon session, we have Antonella Grassi, who will tell us about singularities, matter, U1, and other things. Thank you.
Thank you. First of all, thank you to the organizers for putting together this wonderful conference and also for inviting me. So, I think there is a slide missing. I think there is a slide missing. Oops. But we'll do. I'll improvise. We tried many things. We did not try the first slide.
I think that the only option is to do a double creation.
Okay, then do a double. Yeah. Okay. So we wanted to do single pages, but I apologize. Also, I guess I wrote the slides, and we were planning to have them. I was planning to have them single, but they're all appear on the same page. So the first slide is the setup of F-theories, but with singularities. And I would like to illustrate how singularities arise naturally in the context of F-theory, especially singularities who are interested in mathematics. So the first part, the first slide is this one here, which is the setup of F-theory with a section. So on an open set, on a large set, there is a Calabi-Yau triple on top, which is X, a base B, and a fibration, where the fiber is a T2, a torus on almost all points, and there is a section. So we can go back from the base up to the Calabi-Yau, and outside this set where the fiber is a torus, there is a low side, which we call sigma, the discriminant, where the interesting mathematics and physics happens. Because on this loci is where we wrap branes, 7 branes in this particular case, and this is dual to 2b on the base B. Now, note, there are also fibration without a section. So we don't necessarily have to go up and down. And one of the first reasons to considering this mathematically without a section was that for one fibration, it doesn't have a section, so where we cannot go up, there is an object which is called Jacobian, which for the particular case of Calabi-Yau, and let me stress this only happens for Calabi-Yau. For other type of variety, this is not true. This is Calabi-Yau. The Jacobian is also a Calabi-Yau on the same base. And the discriminant is the same. So the loci where we have a brane wrapped is the same. But this Calabi-Yau is likely singular. Even if we start with something smooth, the one we get here generically actually will have isolated singularity which cannot be resolved without breaking the supersymmetry. So understanding the singularities on this particular Calabi-Yau, when we have this section, singularities of the type I will talk about, it's important also to derive information on the original Calabi-Yau, especially even if when we want to understand explicit bounds. So on the gauge group on the spectra, essentially. We need to go from one to the other and understand the language. But I'm not going to talk about it today. I'm going to make an advertisement for a paper which I wrote about a year ago when I discussed this topic a little bit. But by far is not the last word on it. So this is another case where singularities occur. So given a fibration with section, we know as a result in mathematics, we can write it on the same base as an equation. Typically in a toric variety anyway, this equation is a generalization of the Weierstrass equation. Being in Germany, I think is reasonable to give credit to where it comes from, and sigma, the loci where we wrap the brain, as a very simple equation. And this is where we put the non-abelian gauge algebra. This is a little bit fuzzy, but for now, for what I'm talking about, it's okay. So now, in this case, we can get f and g, and from f and g, we can prescribe, geometrically engineer the gauge algebra. And so a good part of the spectrum, not all. And I'm going to talk about that today. But it gives, but this W is very likely singular. Most often than not, this is really singular. In many cases, when we start with a good prescription, we can get resolve it with a Calabi-Yau without breaking the supersymmetry. But not always, and one of my favorite examples is example in 2016 of this collaboration here, which comes from a particular analysis of genus 2 fibration, where this equation, which looks like it's a Weierstrass form, you can see it's an elliptic curve. But the singularity, this is singular, is very singular, and cannot be resolved without breaking the supersymmetry. Actually, the singularity here, so I thought about it, the technical languages are log canonical, whatever that means. They've not been mentioned in these conferences. Today we heard about KLT singularities or various other mathematical names in disguise, but this one, no. I was hoping that this would appear on the boundary on some moduli, but no. This is really nothing to do. Is actually one example of a singularities that which breaks supersymmetry and is not clear what to do. With the KLT, we can put a metric. With recent words, we can still do flat scalar curvature, but not that one. So that's mystery. Now, okay, good. So what I'm going to talk about today is a paper which hopefully appear at some point. I want to be superstitious, so I'm not putting numbers on it, but where we consider this situation, an elliptic fibration here, coming from the resolution of a Weierstrass model, and the assumption is we have a prescribed gauge algebra, and also we have U1. So in technical term, it means, mathematical term, that the Mordeville group of section is Z. So what does it mean? There is not only this section here, one way to go up, there is another way to go up from X to B. In this way, but actually there are infinitely many. There are infinitely many sections that can go up, infinitely many, exactly how they are the integers. This is a finite generated abelian group, the integer. So the goal of this paper, and this is assigned, so we want to give assigned, an assigned gauge algebra, not group. Today I'm talking about algebra, and the goal is to determine an algorithm for determining the matter, which would be localized and unlocalized, the multiplicity of the matter, and the U1 charges, which they will all appear in the spectrum, if we want to compute the spectrum, and other things. I want to remark that there are many examples in the literature, but by being example, they're ad hoc example, where we're going after this keywords here, which is an algorithm. And matter comes in localized and unlocalized, and again, one novelty here is an algorithm to compute the matter multiplicity, which are it's hard to do with various methods. And also the U1 charges, which I'll make a reference later. And we want to do that in the presence of singularities. And the lingo, the mathematical terms of these singularities is Q factorial terminal. In practice, what does it mean? That doesn't exist a resolution of the Weierstrass model without breaking the supersymmetry. And this is always, and if a dimension is greater or equal, strictly larger than 3, then there is not also smoothing. We cannot X out the singularities without breaking supersymmetry again, in this case. Now, in dimension 3, it's true that there is always an Xing. So the singularities, these terminal Q factorial singularities, can be smoothed in dimension 3. But this is still interesting to do because the singularities are isolated in dimension 3. The same type of singularities will appear in dimension 4. For Calabi-Yau fourfold, it will not be possible to do smoothing. So what we're learning here about the matter localized at point will happen and matter localized on curves in dimension 4. Now, what's a word? What's an example of this Q factorial terminal singularity? We saw it today in various talks. We heard the word conifold. So the conifold is a local equation, a bunch of squares. Typically for a threefold, x1 square, x2 square, x3 square, x4 square equals 0. This is a local equation. And we know by the pivotal pairs about conifold, of some cases, the quintic degenerated. It's easy to get conifold singularities, and these singularities can be resolved. They can be resolved essentially because there is, without breaking supersymmetry, because there is a plane that goes through them, can be resolved. In the case of elliptic fibration, this is typically happen when there is a U1. However, this is not the general case. So there are some squares that cannot be resolved without breaking supersymmetry. And that is the difference between Q factorial, when they cannot be resolved, and not Q factorial, which is the case of the conifold, and we all learn to love for all this wonderful property. So there's these two different cases. The local equation stays the same, but globally, they're different. And they are modeled different. This type of singularities are exactly the singularities that appear on the generic Jacobian. So when we start a model without a section, we want to get a section, generically, we're picking up the singularities, even in the threefold case. So if we want to know something about non-Jacobian, when we don't have a section, we have to deal with the singularities and understand what it does. So, having done the pitch about singularities, what do we do this? So this is like this is what I just said. A good thing for us, even mathematicians and physicists, that in dimension 3, we have anomalies. So there is the gravitational anomalies, the abelian anomalies, the mixed anomalies. These come from physics, but they have a translation in mathematics. They have an equivalent in mathematics. They hold in dimension 3. So we can check that the assignments, what we get, is actually consistent with the anomalies, which is a good check to see for the consistency of the theory. So what the assumption in our papers is we have this gauge algebra, terminal Q factorial singularities, and we assume like a general case. So we assume there is a smooth curve, gamma, where we have branes wrapped. So this is a curve in the base, and then it's generic. So outside of these curves, we just have the fiber are nodes. Typically, they're nodes. And this is the general case. The general case, it's good to run algorithm, to find algorithm rather as opposed to specific example. And the Mordeville group is Z, so we'll have a U1. And the background is there is a paper which we started quite a few decades ago in the last century with Dame Morrison about assigning gauge algebra in this case, this general situation. But we only consider non-abelian gauge symmetry. Then later, with Timo and collaborators, we assumed terminal and Q factorial singularities. So we assumed Q factorial singularities, and we also analyzed various examples. So the novelty in this case, and let's go back here. The novelty in this case that we add also the U1s. So first just non-abelian, then non-abelian with terminal q factorial, and then non-abelian, terminal q factorial, and also the U1 in the general case. And again, this is a general algorithm and not only case-by-case ad hoc computation. So these are the starting point. The starting point is a paper I didn't close the parentheses, on 14, where the fiber is in this particular weighted projective space as a particular equation, and we analyzed general cases and interesting examples. So this is the fiber. So instead of taking it just in the Weierstrass form, like we keep in the plane, we consider with weighted, with particular weights. So that's the assumption. And I want to present now some of the sample findings and some application. Okay, so findings. The first one is when we have a U1, and actually we don't have any gauge group. I learned from my physics collaborators that this is typically called a sanity check, which is reasonable to do, but also in this case we learned something. And, okay, so in this case there is no non-abelian gauge symmetry, so there is, we only have the abelian group, the A1, and we have, so generically the fiber is a node, and at a certain point over this curve gamma, we have charges. They only have the U1, so we have charges against the U1, so the charges are the little number on the bottom. The number here is singularity in quotation mark, because the general fiber, which is a node, a curve, sort of has the equation that looks like this other fiber here. With an A1 singularities than we saw, I guess, this morning. But the fiber doesn't quite often look like this. It's just a bookkeeping method to see what it looks like. And in this case, we have a singularity, and there is a feature which is called attached to singularities. The singularity here is like a conical singularities, and the number attached to it, which is relevant for the physics and the math, is called the Milnor number. And I'm going to talk about it later. This ends up in the spectrum. And this is also another example here where we have a cuspidal, 2 is for a cuspidal, and again we have a singular type, Milnor number 2, so this is different, this is not a conifold, and then we go through various cases where we have various singularities and also charges. Now, a particular case here is the case of the SPK. SPK, K is written in small, and U1, where again we have the charges on the abelian factor, and the singularity here in this point, the fiber, the singular fiber at this point looks exactly like the general fiber. So it doesn't look like by the naked eyes nothing particularly happened, except that this fiber is singular. And the fiber has a singular point, and because it's q factorial terminal, then there is actually a matter representation. Although we wouldn't see it because the fiber looks the same, but it acts like there is a fiber representation. So the remark here, then we verify the algorithm to find charges, which appeared in a paper by our two collaborators in 2022. So they wrote this paper how to compute the charges, which is a bit similar. No, it's different, but in spirit, it's similar to the equation of the sigma of the discriminant to find where the branes are located. And the novel part of this paper is this algorithm to compute the multiplicity of the matter, which we get here, and which occurs which we need to compute the spectrum, not only the matter, but also the multiplicity. So one things that we need to compute the uncharged massless multiplets, which actually we did in a previous paper with Timo, but we also verified here, is that the uncharged hypers, the complex deformation -1 is given by half B3, which is a topological Euler, the third Betti number, which is easy to compute in many ways, for example, in toric setting, plus this number, which is called the Milnor number of a singularity. So the singularity enters in the uncharged matter as well as giving matter, charged matter to some particular points. So the definition is here, and it works only because terminal singularity in dimension 3 are hypersurfaces. So they're always equation. And it can be, the Milnor number is the dimension of this vector space. So we assume that the equation is given by this, which can always be given by this equation in dimension 3. We take the derivative and compute the dimension locally as a vector space, and this is the Milnor number, which has a lot of interesting property, but this is enough for us. And for Calabi-Yau threefold, the Milnor number is equal to the Turino number, which is the number of complex deformation of the singularities. So that was how to compute it, and what was happening in the previous formula. Again, here we check that all these anomalies are satisfied. Last. Yesterday, someone said something like in a talk, think globally, act locally. And so this can be also true here. So the complex deformation, the uncharged hypers, has this writing here. And we can do some simple arithmetic and write and take out, because the Turino number is equal to the Milnor number, we just can take out this factor and add the difference. So this, by our math result, this is the deformation of the singularities, the smoothing, the dimension of the smoothing of the singularity. So now, what is this object here? It's tempting to say this is exactly the dimension of the singularity of the moduli, the deformation that leaves the singularity singular. Unfortunately, we don't know if it's true or not, except in one case, which is the case of the conifold. In the case of the conifold, an argument that comes from both Friedman in the 80s, but Icano didn't even know he did it. So from mathematics, it turns out that this actually, there is exactly a splitting. And then in the paper with Timo, all our paper with Timo, there is also a physics argument, but goes through the orientifold, which also says that in this case, the number, the uncharged hypers, it essentially splits into parts, a local part and a global part. And for the rest, it's an open question. For the other type of singularities, we don't know. So the conifold is special, and I think I want to end up here. So it's the end of the talk. Thank you.